Rajeshwari MJ. She pursued her BE in Electrical and Electronics at the People's Education Society College of Engineering, Mandya. She pursued her MTech in VLSI Design and Embedded Systems at the Sri Jagadguru Balagangadharanta Institute of Technology, Bangalore. Her personal skills lie in good verbal and written communication skills. Her areas of interest lie in OOPS with C++, renewable energy sources, HVDC transmission, digital relays, automotive electronics, advances in VLSI design. She has also had papers presented at the national level, such as the Innovative Architecture for SoC Multi-Core Hybrid Processor, presented at the RNSIT, Bangalore.
Welcome to UGC lecture series of BSc Physics Honours. In this session, we are going to discuss about the digital electronics subject, and we already started the first portion in the digital electronics, that is the topic is fundamentals of digital electronics. Now, we are going to move for the next topic, that is Boolean algebra. The contents that we are going to discuss today are in Boolean algebra are postulates of Boolean algebra, theorems of Boolean algebra. Let us have a definition of Boolean algebra. It is a type of algebra, but it deals with the logical operations. So, what the logical operations will going to perform in different way. So, and this algebra will also have set of rules. Using this set of rules, we are going to simplify the given expression, because if we are going to design any number of circuits, that circuits will be having n number of inputs and n number of outputs. So, we need to represent everything, the output will be always represented with the help of expressions only. So, to reduce this complexity, we need to simplify this outputs, and also while simplification we also able to reduce the components that can be used for or used to design this kind of digital circuits. So, this Boolean algebra is very much fundamental, and it is a must thing that we need to know in a digital electronics subject. Also, we need to know about the combinational logic circuits that we already started in the first basic topic itself, that is AND, NOR or NOT gate. All these type of gates are called as combinational, because why means the combination of two inputs only results in the output, and this type of circuit won't depend on any previous values, and also there will be no storage, there will be no storage element in the this kind of combination circuit. So, this type of circuit will be called as combination circuit, which will works on only present values of input, that will going to work as a combinational circuit. So, we can say the combinational circuits will going to work with the current input and will going to give output for the current input only. Next, we move on to postulates of Boolean algebra. This we need to remember throughout this subject, that is all these postulates will be helpful for solving the logical expression. So, this is the way the postulates are. The first postulate will be 1 and 1, or 1 dot is represent AND operation, plus will represent OR operation. So, we can read it as 1 dot 1, that is equal to 1, and 0 plus 0 will be 0 always, and 1 dot 0 that is equal to 0 dot 1, reverse 1 dot 0 or 0 dot 1, that is equal to 0 always, and 0 plus 1 equals 1 plus 0 is equal to 1 always. The next postulate is 0 dot 0 is equal to 0, and 1 plus 1 is equal to 1. Finally, 1 bar is equal to 0 and 0 bar is equal to 1. These are the things that we need to remember through for entire things. Next, we move on to theorems. There are plenty of theorems that we need to know, because all these theorems will be helpful for solving the complex or difficult expressions to make all this expression simpler. So, first we are going to deal with the theorems, that is identity law. So, identity law deals like this: if it having n number of same or identical variables, all these x or a or b or c, that whatever we are looking here in the slide, that all this a, b or x will going to read as or represent as variables. So, x dot x till n number of x, that will going to lead as x only. If it is having n number of identical elements, that will going to equal to x only. So, another thing, if it is also in represented in a OR operation, x plus x also lead to the x only. So, for the help of example, we can study this rule. Here we a dot b bar plus c dot c will be there, and from this expression and this expression we can take the identical element or common element out. We can express a dot b bar plus c as a one element, because from here a dot b bar and also c from here we are going to take it out. So, a dot b bar plus c will going to lead to a dot b bar plus a dot b bar plus c. Here a dot b bar will going to represent it as b bar only, because this will be a postulate that we already discussed. B dot b bar will be b bar again. So, plus c dot c we applied here the identity law. So, c will be the expression here. So, here a dot b bar, the b bar and b bar will be b bar the output. So, from the postulate a dot b bar will remains here, cancelling one b bar. For next term a dot b bar remains as it is. Again for c dot c we are representing, we are applying c for c dot c here the identity law. So, c dot c become c here. So, for next again the simplification step will be a dot b bar plus c, and for this expression we need to again apply the identity rule, that is a dot b bar is identical as a dot b bar. So, one term we can write a dot b bar. So, finally, we come with the two terms of identical. So, a dot b bar plus c can be written as single a dot b bar plus c. Next theorem is complementation law or complementary theorem. So, here it going to define like this: if two variables, if the two multiplication or ANDing or ORing of two variables having identical variables, one with inversion and one without inversion, will always give to 0 in ANDing, and in ORing it always gives 1. Let us consider with an example. For example, for x is equal to 0 and x bar is equal to 1, apply this to the complementation law, that is 0 is x is equal to 0, we applied here 0, and x bar is equal to 1, 1 is applied. So, 0 dot 1 is equal to 0 from the postulate. Next x is equal to 1, for x is equal to 1 and x bar is equal to 0, we substitute these values here, x dot x bar will become 1 dot 0, that is equal to 0. So, applying this rule for an example, we get to know better. So, a plus b dot c and a plus b dot c whole bar, this will going to give a 0 only, because this entire will going to consider as a one term. If we consider entire thing as a y, this will become y and this will become y bar. If we consider a plus b dot c as y and a plus b dot c as y bar, y dot y bar is equal to 0, same thing as we discussed in the above. So, again another condition, that is a plus b dot c in the OR operation, we are considering OR operation, plus a plus b dot c whole bar, it is always equal to 1. ANDing it is always 0 and for ORing it is always 1. Next law will be the combination law. Combination law deals with ARing or ANDing of a term, or ORing or ANDing of a term which can be the output will be always same if we interchange the two variables. So, if one thing is x plus y, the output can also, that will be also equal to y plus x. So, these two will be same. If we written y plus x or x plus y, that does not mean any changes. So, if we want to express x plus y or y plus x, that is same, remains always same. and same in the ANDing operation also, x dot y is equal to y dot x will always works in the same manner. So, next law is associative law. This going to define like this: if we have three variables like x plus y plus z, x plus of y plus z also equal to y plus x plus z. So, if we OR this first and again this term is ORed with x, does not change if we OR x plus z y, x plus z plus y, and also this will going to equal to x plus y. So, how means if we first OR this and again ORed with y, does not change. So, if we first OR x plus y and then ORed with x z, it is also does not change. So, if we interchange all this ORing also, the term, the expression, the output expression will does not change, or the output remains always same in this condition. So, this will be applied same for ANDing also. Next, we deal the above equation with the help of example, that is a bar b plus c dot d bar plus e bar dot f bar, that is equal to like this. So, if we interchange the inner terms, if we interchange the terms also, it does not change. That is how we can written in a associative law like this. So, the distributive law, the next law will be the distributive law. So, in the distributive law, the distribution of the terms will be in different way, that is x dot of y plus z can also be represented like this. If we multiply x with the this term, that is x dot y plus x dot z, this and this will be going to give the same output. If we express this, and also if we express this expression in this form, the output of this expression and output of this expression will always remains same. And also this can be represented in a ORing form or ANDing form, x plus y dot z, that is equal to x plus y and x plus z. So, this is another form we can represent the distributive law. So, next we move on to important theorem, that is De Morgan's theorem. So, here the De Morgan's theorem represent the sum of the complements, sum of the inputs, identical inputs complement, sum of the complements and its sum, the total input sum complement is equal to complement of sum of each complements, that will going to give a De Morgan's theorem. That is, sum of inputs whole complement is equal to complement of each inputs, that will be the define the De Morgan's theorem. This can also be used for both ORing and ANDing. So, we will take with an example here. So, De Morgan's theorem can be proved like this, that all variables are in a logic 0 state. In that case, what will be going to happen in a De Morgan's theorem, that we know the LHS of De Morgan's theorem will be the sum of the inputs complement. So, x1 plus x2 plus x3 till xn. So, all this will be of 0 value that we are going to give. So, if all will be 0, that will be going to equal to 0 bar. So, this will be equal to 1. So, the RHS part of De Morgan's theorem will be x1 bar dot x2 bar dot x3 bar. So, the inputs the complement sum of inputs complement that is equal to, that is summer or ORing the inputs, summer or ORing the inputs complements, that is equal to ANDing outputs, complements of each ANDing outputs, that will be the RHS part. The RHS will be x1 bar dot x2 bar dot x3 bar till x bar n. So, here also we are going to substitute x1, x2 everything with a 0. So, the output will be 1. So, for 0 bar in the sense 1. So, again 0 bar in the sense 1 till it will go till to the xn bar. So, that is also 1. From identical theory we can write this is equal to 1. So, LHS and RHS is proved as a 1 equal, both are equal. So, De Morgan's theorem is proved. So, next we move on to involution law. In involution law, the complement of complement will be same. If we are going to give any complement or complementary complement of complement, it will going to give the same value. So, if we take any variables having double complement, then it will be the output will be of same as a input. So, next we move on to transposition theorem. Here in the transpositions, in the sense we are going to transpose two things. If we have two terms and in the two terms in any one of the term will be having the same variables with complement, then we are going to write like this. So, x dot y plus x bar dot z, that is equal to x plus z dot x bar plus y. So, this represented where two terms will be having, in any one of the term will be having same identical term and the next term will be having the complement of any term that is present previously. So, here x will be the term that we can observe in two terms, and in the first term there will be no complement inversion, but here in the second term we can observe the x complementary. So, this can be represented using transposition theorem like this, x plus z dot x bar plus y. So, this can also be applied for ANDing operation like this, x plus y dot x bar plus z. So, here also we can observe x and x bar, that is equal to x dot z plus x bar dot y. So, what we can observe from the transposition theorem is any sum of products or products of sum. So, sum of products, this will be sum of products, sum of products in the sense x y and x bar z will be the sum of products, and products of sum, the sum will be here x plus y and x bar plus z. So, this will be the products of sum, both expression having two terms, provided that a given variable in one term has its complement in the other. The given terminal in one term will be the complementary of other. The x we can observe here in one term, that will be appeared as a complementary in the second term. Next we move on to the proof of this transposition theorem. We considered 8th A, that is 8A, that what we are going to discuss in transposition theorem. This we are going to prove with the help of truth table. So, x, y, z we are having different combinations of inputs, and x, y we first considered with the help of AND operation, and x bar z also defined with the help of truth table. So, x plus z and x bar plus y also defined with the help of truth table. So, finally, we come to know x y plus x bar z, the OR operation is done in between x y, this and this. So, OR operation will leads to this output. Finally, what we need is x plus z, x bar plus y. So, this is a LHS and this is a RHS. We need to observe these two expression. So, these two outputs of the expression is same as LHS and RHS. So, hence the theorem is proved. So, what we are basically considered is the terms x. First we need to do the AND operation, a dot x, and next we need to consider this term, that is x bar dot z has to be done. This AND operation is done. So, that is what here this AND operation is done, and finally, in the LHS in the RHS part we need to do OR operation, that is x plus z, and another term x bar plus y, that is also done here with this, and we need to OR this and we need to AND this two to get this expressions, two different expression, and observe the two outputs which will be giving the same outputs. So, this LHS will be going to equal to RHS, hence the theorem of transposition is proved. Next we will take another example, that is L dot m plus n bar plus L bar plus p bar plus, dot q is equal to L plus p bar dot q, that whole in dot L bar plus m plus n bar. So, this LHS and RHS has to be equal. So, how with the help of theorems that we discussed, we are going to consider L is equal to x, this L is considered as x, and m plus n bar is equal to y, and p bar dot q is considered as z. So, substitute these x, y and z value in the LHS. So, we will get for L we are going to substitute x dot for m plus n bar we are going to substitute y. So, x dot y, this term over. Next plus symbol is carried forward, and for p, for L bar we are taking x bar. So, x bar is mentioned. Next dot for B bar, for P bar dot q we are taken z. So, z is carried forward here. So, from this expression we can apply the transposition theorem here looking at this expression. So, for after applying a transposition theorem we can write this expression as x plus z dot x bar plus y. So, after getting this expression we need to substitute the x, y, z value. So, this is the final answer, that is equal to the RHS. So, finally, we proved LHS is equal to RHS. Next we move on to another example, that is using a different Boolean laws and theorems and also postulates. We need to simplify one of the things, that is starting with the Boolean expression for a 2 input OR gate. Apply Boolean laws and theorems to modify it in such a way as to facilitate the implementation of a 2 input OR gate by using 2 input NAND gate. So, what we have is OR gate. With the help of OR gate expression we need to find a writing this 2 input OR gate using only NAND gate. So, we have to modify this expression, OR gate expression, so that we can implement this OR gate with the help of NAND gate only. So, first we consider 2 input OR gate Boolean equation, that is y is equal to a plus b, we can represent the OR gate. So, where a and b are the inputs and y is the output. So, a plus b, that is equal to a, this is what we consider double complementary. So, this will going to give the theorem that we already discussed, involution law, because double bar will always remains the same, in the input will be same as it is output. So, this 2 inversion cancels, a will be remains same plus b double bar. Okay. Next we move on to the De Morgan's theorem, apply for De Morgan's theorem for this, so that we can able to get like this, a double bar dot b double bar. So, this is how we are going to represent the above equation. Finally, applying the idempotent law we can able to write a double bar dot b double bar as like this, a dot b whole bar, because a dot b will be a and b dot b whole bar will be b. So, again it will going to give the same expression. So, this 2 will going to give the same expression. So, from this we are having only the AND operation. So, AND operation in the sense AND with an inversion is there. So, we can able to get a NAND gets easily with this expression. So, we can represent the OR equation easily with the NAND operation with this expression. So, finally, what we get from this expression is, this is the logical gate representation, logic circuits from the expression that we got. So, A is given to the input, A is given to the NOT, that is NOT gate, that is represented as a NAND gate. The output from here is A bar, and here also it is given for a NAND gate that will works as a NOT gate. So, output from here is B bar. So, A bar, B bar, that is again given to the NAND gate. So, A bar dot B bar, that is whole bar, that is what we are going to represent. So, that will going to be A dot plus B bar, A dot B bar whole bar. So, after simplification we can again get the A plus B as an output, that will be the OR expression. The next example is, apply suitable Boolean laws and theorems to modify the expression for a 2 input XOR gate in such a way as to implement a 2 input XOR gate by using the minimum number of 2 input NAND gate. That is what we need to represent XOR gate with the help of NAND gate only. So, we have the expression for XOR gate like y is equal to A bar dot B plus A dot B bar. This has to simplify and modify so that we can able to represent this expression with only NAND gate. Again with the involution we can write this expression like this, A bar dot B bar, for each term we are apply the involution law here, each term double inversion is applied, Again this can be rewritten with the help of De Morgan's theorem. The plus operation comes dot and the whole complementary is given, the inversion is taken for the whole terms, that is for 2 term we have taken inversion. Next this has to be rewritten like this, b can be taken here and a bar plus b bar. If we multiply this b to this a bar plus b bar, again we get back the a bar dot b, that is a bar b dot b plus b dot b bar. In the sense b dot b bar we already know b dot b bar is equal to 0. So, that we are going to give remains the expression a bar dot b bar previously what we have here. So, again this expression is also rewritten like this, a dot e multiplied by a bar plus b bar. So, this can be rewritten again with the help of De Morgan's theorem. So, a bar plus b bar can be written as a dot b whole bar. So, this also rewritten. Only thing that we observed from all these expressions or all these steps is the plus has to be replaced with the dot. How much it is possible to replace the plus with the dot, because and in the sense dot has to be the operation. So, how much it is possible for us to simplify the plus to dot till end we need to do. So, at the end expression we want all the operation has to be in a dot form. So, fine, we can able to get the NAND gate expression. So, this will be the NAND gate expression. Through this expression we can write this logic circuit of XOR gate using NAND gate. So, this will be the input, 2 input a dot a and b, this is given for the first NAND gate. The output expression will be a dot b bar, this is a dot b bar will be the first output from the first NAND gate, and this a dot b bar will be given to the next 2 NAND gate. This will be the input, and again a is given to the one NAND gate, b is given to the another NAND gate, these 2 terms. So, finally, a dot b a b bar whole bar is from the this NAND gate and b dot a b bar whole bar, these 2 term will be get from this 2 NAND gate, and finally, we will getting a bar b plus a b bar XOR representation from the final NAND gate. Let us have a quick summary of this session. That is the different kinds of postulates for that we discussed in this session, and also that has to be remembered for the simplification of the expression, and also different logic theorems that we are already discussed, that is idempotent and complementation and law and commutative law, associative law, and also distributive laws, and the De Morgan's theorems that which is very important, that is represented like this. The products, the ANDing of inputs complement that is equal to ORing of each input complemented components. So, this will going to give the De Morgan's theorem, and also involution will be the expression that is having double complement is always equal to the input. So, transposition theorem also represent like it is like this, x y plus x bar z is equal to x plus z dot x bar plus y. The questions of this session are: define the Boolean algebra, what are the important postulates of Boolean algebra, which are the important theorems of Boolean algebra, explain the De Morgan's theorem with an example. The references are talkingelectronics.com, and the textbook references are Digital Fundamentals 3rd edition by Thomas L. Floyd and Digital Electronics by R. P. Jain. This ends the session. Thank you.